So now what we're going to do is actually give some meaning to these vectors, and we're going to use them to represent forces. So the important thing is that unless a force acts upon something, it's going to stay in a state of equilibrium. Many people make the mistake of thinking that equilibrium means at rest. If I'm driving my car consistently at 100 kilometers an hour, then I am in a state of equilibrium, and I won't slow down or speed up unless some force is applied, either acceleration due to gas or deceleration or slowing down because I put on the brakes. If I don't change the forces in the system, I will keep going the same speed. Being still can represent a state of equilibrium, but it's only one example. So let's consider an airplane that's traveling at a constant velocity. What forces are acting upon the plane? So I'm going to think about the plane being a dot. So there's forces acting on this, but they are all balancing each other if the plane is traveling at a constant velocity. Well, the first obvious force is gravity, which is pulling down on the plane. In order for the plane to not be falling, there has to be an opposite force to that. We call that lift. And lift is generated by wind moving over the wings, which creates pressure moving up. So those two are balanced. But this is kind of moving in a forward direction, but at a constant velocity. So from the plane's propellers or engines, depending on what kind of plane it is, you get something that's called thrust. So thrust is pushing the plane this way, so I'm going to represent it as a force going forward. Now, if thrust were the only thing acting on the plane in a horizontal direction, it would keep accelerating, accelerating, accelerating. There has to be something to stop the plane from accelerating, and that's the pressure of the wind pushing on it, which in this situation we call drag. So there's four forces acting on this airplane, and if it's in a state of equilibrium, they're equal. If I apply more lift, or if I thrust more forward, then it's going to change and it's going to speed up. And then which in turn, a lot of the times if you tip the wings, will create more lift. So unless something in here changes and a force compels it to change, it will keep traveling at the same height at the same velocity. An important concept for this is the idea of newtons. Newtons are going to represent the units of our force. And it's go to the unit of acceleration for gravity. So an object falling will accelerate at a rate of 9.8 meters per second. So then they came up with that. It's going to mean 9.8 newtons is how much force is on a 1 kilogram object due to gravity, because that's how much it would be accelerating. So all of our forces will be measured in newtons. So Jake is pulling his friend on a toboggan with a rope that makes a 25-degree angle with the ground. If he's pulling with a force of 70 newtons, what's the horizontal force being exerted on the toboggan? So again, they're just comparing how hard he's pulling to how much gravity would be on something. I'm going to start with a diagram. So there's my toboggan. There's the rope, and the rope is pulling this way, and the force in the rope is 70 newtons. Hopefully the toboggan isn't traveling up into the air. The toboggan is actually traveling that way, and the angle between there is 25 degrees. Now, there's two things happening. Because this is acting on an angle, it's actually pulling up on the sled, but the weight of Jake's friend is keeping the sled in place, but it's also pulling it forward. So there's two components to the 70 newtons because it's on an angle. There's a horizontal component, and there's actually a vertical component. So sometimes they're represented as the force horizontal and the force vertical. They're asking for the horizontal force. Well, because horizontal and vertical are always 90 degrees to each other, we are going to be able to SOHCAHTOA this. I know the 70 newtons, which is my hypotenuse. I'm looking for my horizontal force, which is my adjacent, so that's going to be cosine. So the cos of 25 degrees, because that's my theta, is A, which is my horizontal force, over the hypotenuse, which is 70. I'm going to bring the 70 over and multiply. So I'm doing 70 times the cos of 25. So 63.4 newtons is the force that's being exerted horizontally on the toboggan. So 6.6 newtons are pulling upwards, but it's not actually going up because of the weight of Jake's friend, and 63.4 newtons are pulling it forward. Another toboggan question. So, two people are towing a toboggan by walking side by side. Each exerts a horizontal force of 60 newtons. Each rope goes off to the side and makes a 20-degree angle with the line of motion. Find the force that is pulling the toboggan forward. So I'm actually going to do a bird's eye view of this one. So there's the toboggan. There's the forward motion of the toboggan. Here's one force of 60 newtons, and I know that angle is 20 degrees. Here's another force of 60 newtons, and again, that angle is 20 degrees. Now, the horizontal force, or the force pulling the toboggan, is the resultant of these two forces together. So I'm going to use the triangle inequality, and I'm going to take this one and move it up there. So now I've created a triangle. It goes tip to tail, and then my resultant goes from the beginning to the end. So again, that's 60 newtons. That's my resultant. I want this angle. Well, here's half of my parallelogram. There's 40 degrees there, so that leaves 140 degrees in between my two forces, and I'm going to apply cosine law. So the magnitude of the resultant squared is 60 squared plus 60 squared minus 2 times 60 times cos of 140. I'm going to type that into my calculator, and then I'm going to remember to square root it, because typing this into my calculator gives me the magnitude squared. I just want the magnitude. So 60 squared plus 60 squared minus 2 times 60 times cos of 140 equals, square root my answer, and I get 113, or 112.8, or 113 newtons. Now, the forces together actually equal 120 newtons. But because they're pulling in opposite directions, some of the force is lost working against each other. So that's why our actual force that's moving it forward, which is 113 newtons, is less than our 120. So an equilibrium is equal in magnitude to the resultant, but opposite in direction. It counterbalances the resultant and keeps an object in a state of equilibrium. So now, if we think about what's happening to this system up here, the sled is moving forward and a force of 113 newtons is being exerted on it. If that were the force, the only force being exerted on it, it would continue to accelerate. There has to be something here, an equilibrium, to keep this toboggan moving at a constant velocity. And that force is going to be friction. Now, if it's snow or ice, friction is considerably less, but it is an equilibrium force in this case. Without this friction holding the sled back, the friends would continue to pull it faster and faster and faster. But because friction, the tension between the bottom of the sled and the surface of the ground is there, whether it's a high or a low level, it counterbalances the 113 newtons.